Today we're going to look at the vector network analyzer, but we're going to continue looking at the DG8SAQ, but from the software perspective. So in the previous video we looked at how to physically connect this network analyzer to a Tesla coil, and various different cabling options, and how to go about calibrating from that point of view. Now we're going to have a look at that from the software point of view. I've got the same coil on the bench here that we were using in the previous video. The setup is otherwise the same as it was. So I'm not going to cover in this video the installation of this. That's covered very well in the manual. I didn't have any problems when I first went to install this, and that manual shows you installation of the driver and the software. You can obviously get an update for the software online, and then connecting by USB cable the device to the computer, and then after that the process of actually getting it configured and installed in relation to the audio devices that need to be configured in the computer, for which a driver is supplied. So I've done that already. So I'm assuming that step has been done, and I've got the VNA connected now to the computer. So when you open a software, this is the default set of things. You've got options in menus along the top here. I've currently got S11, magnitude of impedance and phase selected as traces, although I'll go into that in more detail. This is the start frequency here, the center of the sweep, and the end frequency. So currently set to 100 kilohertz, that's 0.1 megahertz, up to 5 megahertz at the far end, which is just what I had configured last time I was using it. The buttons here, continuous and single sweep. Obviously, if you set it on continuous, then it's going to keep taking sweeps. When it gets to the end of a trace, it just goes back to the beginning. Single sweep is obviously a single shot trace. There are various other settings, and you can click on things, and we'll get into that as we progress in the video. So first of all, when I first open the software, I check in the setup. There's a warning about if you change things in the setup, then it may affect your calibration. I go to this screen, which is the audio level tab, and we can see there the audio signal. I just test that, and both of those should have the sine wave as it's shown, and they're just gradually either processing downwards or staying still, but we can see that they're being updated. So that shows that the VNA is connected, the drivers are working. Stop that, close that, and then I should be able to just take a single sweep. At the moment, the VNA is just open circuit, and I haven't done any special calibration things at all. There we are, that's one single sweep. If I put it onto continuous, it's going to keep progressing across the screen, then back to the beginning. Okay, now one thing I did forget to mention in the previous video, when we were setting up the connection and looking at cabling and how to work with the Tesla coil, I did not mention that one has to be very careful about how one connects this device in relation to whether you've got your generator connected. The inputs to this VNA are 0 dBm maximum, that's 1 milliwatt, and no DC. So 0 DC, 1 milliwatt RF are the maximum inputs, unattenuated inputs that both the TX out and the RX in. and obviously if you do put more than that, then it could risk damage to the front end amplifiers of the equipment. Now that's not very compatible with Tesla coil generators. 1 milliwatt is exceedingly small in that relation. I mean, it's very, very common to run a Tesla coil at 200 watts and above, and the two are not compatible. And it's surprising how easy it is. I've almost done it a couple of times myself, is to have your vector network analyzer connected to the Tesla coil and the generator connected to the Tesla coil, and obviously to turn on the generator while it's still connected. Then one has to find another use for the box because the VNA is not going to work after that. So that's something that needs to be taken care of. Okay, back to the software. So the first consideration that we need to make here is what is the frequency span that we're going to measure. Now, as I spoke in a previous video, most Tesla coils that I've ever worked with, or of this nature, or if you're working in the HF ham radio band, then the band of interest really goes as low as 30 kilohertz and up to around about 30 megahertz. So that's really the band of most interest. Obviously, it's well within the capabilities of the VNA that we're using. The primary band for this VNA is somewhere, well, it says 1 kilohertz to 1.3 gigahertz, but the primary band is 1 kilohertz to 500 megahertz, and then there's overclocked band from 500 megahertz to 1.3 gigahertz. So we're working in the primary band. That's good. We've got the best accuracy. So first of all, if we have a look at the range that we want to take it over, well, I want to start by taking a wider scan. That shows me, for example, I mean, I've designed this cylindrical Tesla coil so it works in the 160 meter band unloaded. So the middle of that band, that's a 1.8 to 2 megahertz. So I've nominally arranged it to resonate, free resonate around about 1.9, 1.95. But what I would like to see is I'd like to have a look at a wider scan to start with, so I can see what features there are, and that gives me a good idea about what's going on with this coil right from starters before I narrow in on and look at in more detail. So I generally set the lower to 0.1 megahertz. I find that unless you're doing very narrow scans below 100 kilohertz, you need to calibrate very carefully over narrow bands to get good results from this VNA. So 0.1 megahertz is the lower end, and if I double click on any of these, I'm going to bring up a box where I can edit these things. So start is 0.1 megahertz. We've selected units here, megahertz. Stop, we're going to put that up at, say, 25. Everything else is fairly, one can leave. You're doing it across 10 divisions. Do that, and we see that down here that's changed to 25 megahertz. Now, by automatically changing that, I have invalidated my local, whatever calibration I had before. That calibration doesn't necessarily apply, and I'll come back to talk about that in a minute. The other thing we've got to consider is how many data points it's going to take from the start to the end, and we do that by going into settings, and select sweep, and here we can see that it's telling us a number of data points. I was using in my previous measurements 2048, and the amount of data points obviously affects how fast the sweep takes. So the time per sweep here, it says 2.73 seconds. So that's the time taken to go all the way from 0.1 kilohertz up to 25 megahertz. Now, there are various considerations in that time. If you're doing real-time continuous sweeping, you might want to make that very low. I think the lowest, let me, 512. Yeah, 0.68 seconds is about the fastest scan I can get. I prefer more detail, 2048. I think the maximum is 8192, and then you're looking at time per sweep, almost 11 seconds. That's quite slow. So for this level of detail, 2048 is fine. If you wanted to go up a bit more accurate, you go to 4096, 5.5 seconds. But for both static and dynamic work, I find 2048 to be more than adequate, 2.73 seconds. So we've set that. Now we are ready to actually have a look at the calibration itself. So we've set the sweep, we've set the number of points, data points that we're going to take in that, and hence the sweep speed. So let's open up the calibrate menu, and this is the standard calibration, and we have in here the reflection calibration. That is to do with everything to do with S11 and S22 if you're taking that measurement with the VNA connected the other way around, and the through calibration, so everything to do with S21 and again S12 if you are got it reversed around. This VNA can take a two-port measurement, so it can measure S11 and S21, but in order to take the reverse S22 and S12, you would have to reverse the connections, so it doesn't take all four of those network parameters without changing the connection configuration. But in this case, we're really only concerned at the moment with S11 and S21, and even more in this video, I'm just going to do S11. I'll come back to S21 in at another time. So looking at our window here, first of all, we see if we look at the reflection calibration, we have a green M in the center with a circle with a red dot. Now the green M shows us there is a basic master calibration. So that means that when I first installed this from the instructions or subsequent time, I did a full bands master calibration from 0 all the way up to 500 megahertz, and that forms your basic background calibration. That was calibrated just to the SMA terminals, both for the output and for the input. So we see that master calibration applies to the reflection calibration and for the through calibration. Now, if I didn't have a master calibration, so if I come here and I turn it off, it would be looking like this. Now that's no calibration at all. So even if I don't calibrate now, I am taking uncalibrated results, and I can therefore not rely on the parameters and values that the VNA is giving me for the measurements that I'm taking. So having a master calibration means that the machine always has a basic calibration, but that's fine. So for example, I can obviously save those. Here you can see what I've got. Just pull that onto the screen. So that master calibration, I did that originally in 2015, and that's just for the box. And one can do that as many times as you want. But since I always calibrate locally, so for the sweep that I'm actually doing, that will override the master calibration. So we'll close that. I'm going to turn the master calibration. Well, I'm going to load that master calibration again, open that, and we see we go back to the green M. So to do a full calibration, which I would thoroughly recommend before taking any sets of measurements, and it's also good practice to take a reference at the beginning and a reference at the end to check how that calibration is over the time period that you're taking measurements. So very simply, what I've got connected to the VNA is I've got the SMA to BNC adapter that we looked at before, and I've got the high quality Hewlett-Packard BNC cable, and I've got the BNC to dual banana plug inputs connected to the primary coil of the cylindrical coil on the bench. Now, what I'm first going to do is I'm going to calibrate just to the end of the BNC cable. So the plane of reference that I want for this calibration is the end of the BNC cable, and that would be my basic calibration for the set of results that I'm going to show here. So first of all, I come along here and I'm going to connect a short. Okay, so I'm going to connect the short to the end of the BNC cable and press OK. Scans across. Okay, now that's turned fully green, so it means I have a valid calibration for a short circuit between 0.1 megahertz and 25 megahertz. Now I go to the next stage. I need to calibrate for an open circuit, so I'm just going to remove that short and leave the cable, the BNC cable, open. It's good. And I'm going to do the same for the load. I've put 50 ohm termination, calibrated 50 ohm termination on the end, and I'm going to run that. Okay, so everything's turned green and the calibration is turned on. So obviously I haven't done the through calibration, and I'm not going to do that at this stage, but you would proceed in the same way, but obviously you need to use a cable between the input and the output. I'll come back to that at another time. So having got that calibration, I can now close the window. And here is, I like to do a reference test to see how good that calibration is. So that means I've left the 50 ohm termination on the end of the BNC cable, and I'm just going to take another sweep. That looks good. It looks standard. The blue trace for impedance is off the bottom. Just going to rescale. Now, to rescale something and put a trace in a particular part of the screen, then we come and we click on the reference in the bottom right there, and we can see it's currently set to 20 or 2,600 ohms per division, which is quite a large scale, and the reference level is set to 50.1 ohms. So I'm rather going to set this to about 10 ohms per division, and I'm going to set the reference level to say 40 ohms, which means we'll put we can see it's appeared here. I've put my line there just one division above of the base. So this is 40 ohms, 50 ohms, 60 ohms, it's 10 ohms per division. Now the phase is set here. Again, I could set that if I double click there. The reference level is set at 0, so 0 phase, and 6 divisions above the base. So 1, 2, 3, 4, 5, 6. That's the reference line there, and it's set to 60 degrees division. So that's 60, 120, 180, and that's minus 60, minus 120, minus 180. So now we can have a look at that. Now we've scaled those things, and I've done such a simple scaling. Obviously, I'll show you more about how to do scaling later. But now we have a straight line at 50 ohms for the magnitude of the impedance. Actually, let's talk about the parameters that we're showing here. This is what we are displaying. And because we're doing a one-port reflection measurement, S11. Both of these parameters are set to S11, and I'm choosing to look at the magnitude of the impedance is the blue trace, and the phase of that impedance is the red trace. Now I could turn off the phase, for example. I could turn off everything. I put that back on. Now also I could change what I want here. Now this actually, there's a lot of different things that you could choose to display here. So if I look at impedances, I could show all of those things. Actually that's off, slightly off the bottom of the recording. We'll just look at what we've got along the top there. So the real Z, the imaginary of the impedance, the magnitude of the impedance, the capacitance, the C, the inductance L, and there's a whole, whether it's parallel or series or the Q or the standing wave ratio, there's a lot of different ways which I can show that data. So I measured S11, and the calibration that I've now applied allows this software to show the output in many different forms. And that's a very valuable thing to be able to do. It's handled inside the software. I don't have to be concerned about that, but I just do need to check at the beginning before I take unknown measurements, and at the end that my calibration is correct, because the parameters that I'm reading off of here are dependent upon the quality of that calibration. So for most of my measurements, I use the magnitude of the impedance and the phase. Those are the basic cornerstone of being able to look at the AC small signal characteristics for Tesla coils or antennas or whatever type of network it is that you're actually measuring. Now, the other thing we also need to look at is how the grid is set up here. I mean, here I'm taking a Cartesian, I'm looking at this data in Cartesian form. So in other words, it has an X and Y. I've got frequency along the X-axis, and then I've got the magnitude of impedance on the axis here, and I've also got phase on the Y-axis as well. So I've got two different Y-axes here. Now, I can also display this data in other forms. I can display this in polar form. I can display it as a Smith chart, and all of that is selected via what I've got here. So in other words, what I've got that set up to. So again, if I right click, that menu slightly goes off the bottom of the recording. If I scroll down these various options that I've got here, then it allows me to change the various settings of what I'm showing there. So for example, if I might select Smith, let me just take away the phase plot for a moment so we can see. And so we're actually now looking at in a Smith chart. I'm not going to go through the details of the Smith chart at this stage, but you can actually display that detail on the Smith chart. And also you can select others in there. So there's quite a lot of different options in how you want to display. I mean, the most useful for beginning and that I use is to show the magnitude of the impedance Z and also the phase of that. So if I come down back here, I'm going to select there. I'm going to go into other sorry, impedances, slightly off the bottom, and I'm going to select the magnitude of Z, and that brings me back to here. So that allows us to get our display set up the way that we want it. So if we now look at actually what we've got here, I'm just going to run that again, scan it across. So, and to actually see we know that that's now 50 ohms. But if we wanted to add a frequency marker there, I'm just going to add a normal. So to get that menu, I right-clicked anywhere on the screen. I could do it here, here, and you've got a whole set of things that you can select here. It allows you to affect the way things look. This allows you to select grid options. So in other words, how your Smith chart will look, how your Cartesian grid will look, and it lets you select colors, sizes, thicknesses of lines, all of those kinds of things. Again, you can do it also for the traces. This shows you what the grid color will be, the Smith chart grid color. You can see the traces I've got enabled here. I've got a blue one and a red one, and you can configure all the details in there. Now, here I want to add a marker. So that's going to follow a normal one. And there it is. It appeared there. I can drag that around along the line, and you see the data for that is here. I can click on that, move that around somewhere else, and we could see that where I've got, so point 1, marker 1, is positioned at 12.45 megahertz in the sweep, and this is the 50 ohms, and the phase is minus 91.52. And as I drag that along, it's going to change in real time. That shows us our 50 ohm calibration across the frequency band, just varying there slightly by 0.1 or 2 of an ohm across the band. Now the phase, now this, if we think of the output of the vector network analyzer is 50 ohms, and that's its output impedance, and we got a 50 ohm termination. So we have close to a perfect match. The characteristic impedance of the B and C cable between the two is also 50 ohms. So we should have a very well terminated and matched transmission line here. And in that scenario, and a very good match, this is how the phase looks. So we don't just expect it to be a line at 0. Because the match is so good, it is just flicking backwards and forwards as the vector goes round and round from, in this case, plus 180 and minus 180. Now, obviously, we would normally expect a phase transition of this to be plus 90 and minus 90 in the imaginary. But this VNA considers the whole 360 degree rotation. So phase is displayed as plus 180 and minus 180 transition. So here the phase is just whipping round as the perfect match. Nothing is reflected back, so there is virtually nothing to measure that comes back into the reflected mixer, and therefore the phase is just flicking backwards and forwards between plus 180 and minus 180. That's characteristic of in a vector network analyzer of a near perfect match. I'll just take another sweep of that. Okay, so this shows that over that band, our vector network analyzer is set up correctly, and we're going to check that calibration at the end of the measurements as well. So I'm now going to disconnect the termination, 50 ohm termination, and I'm going to connect the BNC cable to the primary of the cylindrical coil, which is set up in exactly the same way as it was for the previous video. And we'll just take a sweep. Okay, now we're going to need to, you can see that we're going to need to rescale here. So if you're looking on the screen, there are lots of transitions that go off the top and the bottom of the scale. So the easiest way to do that to start with is simply to come up to the top here where it says 10 ohm division, right click, auto scale. Same for the phase. Actually, I'll leave the phase on that basis because it allows the two traces to be separated. And here we can see our basic measurement. Now, I like the line thickness to be a little bit thicker. It makes it easier to see. So I like to increase the line width to 2. Actually done it already. Actually not the grid, sorry, that was the grid. Keep the grid at 1 and the trace width at 2. So it makes it a little bit easier now to see against the background. Take that scan again. And that is our broader scan. People that are familiar with my website will recognize that I take quite a few of these to characterize the various setups and coils and considerations and matching and everything I do in the experiments on the displacement and transference of electric power. So we've got one marker at 1. This is blue line is the magnitude of the impedance, and the red line is the phase relation of that impedance. And we see we have a number of interesting features here between up to 25 megahertz. This here being the fundamental resonant frequency of the secondary coil, and now we're going through its harmonics. This is the second harmonic, third, fourth, fifth. This is the second odd harmonic. So, and corresponding phase changes as we go along. Interestingly enough, this big peak here is as a result of the primary. We can't see the primary self-resonant transition on this because it's actually up above the 25 megahertz that we set. So now, if we want to have a look at some of the detail of that by using the markers, if I want to get an idea about what the resonant frequency are, I'm going to draw that marker down, position it there somewhere there in about the phase change. I want to get a little bit more accurate, so I'm going to zoom in on this trace. That's going to get us somewhere in the right in the transition, or maybe at the top of the transition. Zoom in again, so I can put my marker right in the accurate point I want at the top there. Unzoom. You see now our marker is at the top, and let's drag this somewhere where we can more clearly see it. 2.52 megahertz. So the secondary seen through the coupling of the primary. We have to remember now that we are looking at the secondary. We are not connected to the secondary directly. We are coupling through the primary, and that of course has a very big impact on what we measure. This is when we take measurements like this, we are effectively looking at what the generator will see. So this is the impedance relation that the generator will see. So the VNA here is acting as though it were like a generator, and when we put our whatever high voltage generator we might be using, whether it be spark gap or a vacuum tube or pulse generator or any other kinds of high voltage generator we've arranged for our experiments, this is the impedance, the input impedance of our Tesla coil that the generator is going to see. And it's those things, that this information that we can use to arrange our generator, to drive the Tesla coil or the TMT system at the right frequency. We can arrange matching networks in order to match the generator more effectively to the input impedance, so therefore ultimately we're able to transfer more power from the generator to the Tesla coil or TMT system. And in doing that, this type of AC analysis, and it's a small signal AC analysis, and that's something that I'll come back to, because obviously that's different from the very large signals that we actually apply from the generator. There are differences between the small signal analysis and the large signal performance, but we won't worry about that too much at the moment, since we're looking at how to use the VNA to give us an idea of what the overall input impedance would be. But now, the marker at point 1, that is how the generator sees the system. And that includes the coupling with all the characteristics of the primary, all the characteristics of the secondary, and with whatever coupling factor they have between them. That's very different from if I was to measure the secondary coil just on its own. So that would give me details about how that secondary coil resonates as a free resonator. And for that, as I showed in the previous video, I need to use series fed. Okay, so that introduces the up to this point the basic aspects of the software. What we'll do now, I think, is we'll home in on this area here. So I'm going to change the width of my scan to be not 25 megahertz, but 5 megahertz. So to do that, I simply come here, change that from 25 to 5, close that. Obviously, I've got to rescan that. It hasn't updated the data at this yet. I've just changed the scan range. But also, as a result of that, I'm going to keep the number of points the same, so 2048, but I am going to go and need to check the calibration. Because if I look now, we're not green anymore in the calibration. So by changing the frequency range, although I've still got the master calibration here, I have invalidated the previous calibration that I took. So what I'm going to do is I'm going to recalibrate again. Put the short on, rescan, open circuit, rescan, and a load. Okay, so we recalibrated, we scan that load again. Just have a check. There we are. We've still got that marker there. Obviously we auto scaled, so the position of our line has changed, but if we look along, it's basically 50 ohms again, so our calibration is good. Okay, so then I'm going to reconnect the BNC cable to the Tesla coil, the cylindrical coil, and take another sweep. And there is our fundamental resonant frequency of the secondary seen coupled through the primary. And I'm going to auto scale magnitude, and then I'm going to adjust it so it sits more nicely. So double click on there, and I'm going to set it to 200 ohms per division. The reference level is 0 ohms right at the bottom here, and that's fine. So the bottom line is 0. Close that, and now that gives me a good view of both results. And now I'm going to add some markers so we can take a more detail. I want to have a look at this curve, so I'm going to home in on, try to zoom in on there, and that allows me to move my marker right up to the very peak here. Zoom in on that even further, and I can adjust my marker. I'm going to put it right in the center there. Unzoom. I'm going to add another marker, and I'm going to put that right down at serial resonance there. Let's open up that right into the bottom of that dip. There we are. More. I'll put it about there. So now I've put markers on those 2 points of interest, and we can see from our data here what those two things look like. So now this is typical of the characteristic of a primary coupled Tesla coil, so two resonant coils together. Obviously the self-resonance, the primary I haven't got tuned here with a tuning capacitor, so its self-resonance will be at a much higher frequency. We see it was even much higher than the 25 megahertz. So the phase change, although we saw the impedance, the magnitude of the impedance peak for the primary at big one in the center, we didn't see the phase change, which was off the top. So because there's no tuning capacitor on the primary at the moment, parallel tuning capacitor, it's basically just open. So we have an inductive coil. So here we are coupling to the secondary coil, and it's a secondary coil resonance that we're looking at here, seen through, reflected into S11 and hence Z11 into the vector network analyzer. And this is very characteristic. It's almost like you have a parallel point and a serial point for that resonance, very much similar to what you get with a crystal resonator, which has both a parallel and a serial resonance. So we have that high impedance peak, one at 2.42 megahertz, and at 1.4 kilohertz is the peak. That peak would no doubt be somewhat higher than that. We'd have to take a much narrower scan to find out what the height of that peak might actually really be. And then we have a serial point down here, which is in line with the phase change. As I've said in previous posts, that phase change, position at phase change is very associated with wire length, and of course that's also reflected again through the primary. That's at 2.51 megahertz and is only 9.84 ohms at the bottom there. And this is very typical of both a cylindrical and a flat coil, a Tesla coil arrangement, where it's arranged as a loosely wound free resonator rather than a tightly wound voltage accumulator, as in a very tightly wound Tesla coil. So what we can show now is I'm going to do the same as what I did in a previous video and show what happens when we change the coupling, and then we can see how that works with the software. So to do that, I'm going to set it onto continuous, and then we see it moves over. First of all, I'm going to put my hand near the secondary coil. I'm not actually touching it, I've just got my hand close. Now I'm about a centimeter, my hand is away from the coil. Now I'm actually touching the coil. Damped that oscillation, loaded the coil, pulled that resonant frequency down, and pulled down the Q. You see the magnitude of the impedance, the blue line has really reduced. That's put loading on that coil, and it's now no longer freely resonating. It's affected by the proximity of another partially conductive medium that's in the form of my hand sitting on the coil. I remove that again, and we go back to where we were, and we see the markers are still in the correct places. So we went right back. I'll put my hand on again. We see the markers essentially stay where they were. Bring it back. And markers are back to where they were. So now what I'm going to do is I'm going to gradually pull the secondary coil away from the primary, and we see the results of actually reducing that coupling between the two coils. Gradually shifting them apart. It's about 10 centimeters. We can already see starting to collapse. Very slight changes in the shift of frequency as well, showing that the frequency that the generator sees as a result of those two coupled is also dependent on the coupling that's going on between the two, because the proximity of them affects that. It's about 30 centimeters apart. It's almost the out of range. Let's just take it quite far now away. And we would barely even, it's there at a distance. We have about 75 centimeters between the two. Secondary's at the end of the bench, primary stayed still. I take it away completely off the bench. Okay, so we're still scanning. I've taken the secondary right off the bench. And we can see that it's disappeared. There is no coupling between the primary and the secondary. So I'm now going to bring the coil back on again, pretty much where it was before, about 75 centimeters away. It's a very slight kink just between 1 and 2. And if I move it relatively quickly, back down to about 30 centimeters, now we see the coupling increasing. Down again. That's it. We're now increasing. That's back to where it was initially. See, the markers are back right where they were. I got it in the same position, and then I'm going to slide it right in. The nice arrangement of these cylindrical coils is that the primary can be moved right inside. Now you see that changes significantly. It's pushed the series point up. In other words, as those coils interact very, very strongly now. The coupling's quite tight. The beating between them is quite a lot. We see we've separated further that phase transition and the peak and the trough in the magnitude of the impedance. Pulling it back out again, I'll do it slowly. We see how that take it all the way back to where I started, which is just there. We see the markers are back, peaks are back where the markers were. So that gives an idea of how to use continuous sweep and how the properties of Tesla coils, although I'm not going into detail here about the properties of all these coils. This video is all about showing how to use the software in order to be able to demonstrate these and measure these kinds of properties with the vector network analyzer. So I'm going to turn it off from continuous, and what I do want to show is I want to show the secondary coil connected a series fed connection, so we can actually see the actual properties of the secondary coil as they were designed. Now, if we look at the before we move on to that, if we look at the current properties there that we see, this is how the generator would actually drive it. So the frequency that this coil would be resonating in this mode, provided that the generator was tuned to match its it would resonate and oscillate strongly at 2.42 megahertz. So this point here, if I was to feed back and use something like a vacuum tube oscillator with feedback on it to drive this, then it would automatically self-resonate at that point 2.42 megahertz. And if I had a way of tuning that, which a simple way of tuning that, as shown many times before, is to put a parallel vacuum variable capacitor on the primary, which tunes the primary, and then you can very fine-tune this system with those peaks moving around. And that makes for a very fine-tuned TMT system, and that's what I do in, say, posts on the transference of electric power, and so where I'm able to tune the TMT transmission system to behave in different ways. So either to dissipate its power within the single wire transmission medium, or to very accurately tune in a high Q system the transmitter and the receiver Tesla coils connected by that single wire medium, and then transfer the power into the receiver load. That's all possible, and it's all really made much more straightforward and easier to do that and get the maximum power transferred by using a vector network analyzer in this way. There's just so much data that can be obtained from this. So I'm just going to pause here. I'm going to rearrange the coils so that I can take a reading off of the series fed situation. Okay, so I've changed the coils around. I've taken the primary away. I'm just using the secondary coil now, and I've set it up in a series fed arrangement, exactly as I did in the previous video. I've connected the negative terminal of the output of the VNA to the my dedicated RF ground, as I did in the previous video. And I've got the other side, the positive inner terminal of the output of the VNA, connected by a short lead to the base of the secondary resonator. Now, the first thing I need to do is obviously take a calibration, because I've changed everything here. And for the sake of this, I'm going to calibrate as I did before at the ends of the leads. So I've got the splitter connected to the output of the VNA, and I'm going to do that calibration again exactly as I did it in the previous video. So let's do that. I'm going to keep the frequency range the same and the number of points. I'm going to go into calibrate. Now it's still showing an active calibration, so I'm just going to do it again. So place a short, measure that, open circuit, and then the 50 ohm load. Okay. I'm going to take a single sweep of that. It's fine. I've got a 50 ohm external load there. And we're also connected to ground as well. Reconnect that onto the coil. So we are now ready. We'll take another sweep. Okay, so now in this situation we're going to need to rescale. So first of all, going to auto scale here. That's a very, very large peak. But we'll have to reduce that. Phase change is quite small. Let me auto scale this. Okay. All right, so now I'm going to manually set these up so they're not just at arbitrary values. So first of all, I'm going to set the reference level at 0, and I'm going to reduce that to about 20. 1, 2, 3, 4. Maybe a little bit more than that. Ooh, wrong way. Yeah, that'll be fine. Now the other one is a very, very sharp peak, and I want to look down in this region so we can see. But before I do that, that gives you a very good idea of the very, very high Q of this resonator and the ability of the VNA to be able to see that. We look at this peak here. And if I go in here and look, it's a very, very sharp. I would have to put a very, very accurate, if I wanted to see that in more detail, make a very small sweep across there with many points in it to see how that would look. I want to look at this region because this is a series fed measurement, so I'm looking for the series resonance circuit to get the truly accurate resonant frequency of the secondary coil here. This is a series fed thing. I've got a resonant coil sitting on top of the output of the VNA like it was an aerial. Now when we reach resonant frequency, obviously there's a series resonance circuit. The inductance and capacitance will balance each other, cancel each other out in a way that we'll just be left with the internal resistance of the coils sitting on top of the vector network analyzer. We want to look at that series measurement down here. So I'm going to rescale this to look into that region. I'm going to make it say 100 ohms. That's, or even a little bit more. Say, let's make it say 2000. Gives me a good, or even less, maybe 500, like that. Too much. 1000. Okay, gives me a good view. Reference level 0, 0 at the bottom. And here now, if I bring that marker 1 right down into that series resonance, right down into here, right in the middle of the phase, unaffected by the primary now. Let's go even deeper into that. Really find out where that resonance is going to lie. I'm going to put it about there. That's actually the minimum, somewhere about there. Right in that well of that series resonance. There's the phase change. This is the series resonance minimum for our secondary coil. And if we have a look at that, 1.97 in the 160 meter band. The 160 meter band with nominally 1.8 to 2, and we are there at 1.97 megahertz. And there is there's no additional wire extension on the base of that resonator or anything connected to the top end. So we're just allowing it to free resonate without any other influences, particularly the coupling of the primary. See how much difference that makes now when we just look at the coil itself. This gives us quite a clear indication of how that actually resonates. And we look at the impedance, 84.75 ohms at that resonance dip. Obviously we're sitting on the 50 ohms. This is a series fed measurement. The 50 ohm output impedance goes between ground and the top there. So that is a series fed measurement, and we can measure any of the coils like that. So in effect, we are sticking a coil on top of the VNA with minimum influence, minimum coupling, and that allows us to measure much more truly the properties of the coil itself. But of course, in running, we're not able to actually do that. I mean, we can't just stick the coil and drive it that way and expect to couple lots of power through it. We need to magnetically couple the magnetic field of induction between the primary as though it in the transformer effect to the secondary, and then we can pass large amounts of power. We can make those oscillating currents in the primary very large, either sinusoidal or pulses. Obviously, ideally an impulse discharge there, and we can get very, very large responses in the secondary, as we've seen in some of the previous experimental posts. Now, something also that we want to be able to do with this software is to be able to save this data so we can come back and we can work with it at a different time. So we can quite easily do this now that we've taken this response. We can simply go up to File, Export Data, Trace, S11, Real and Imaginary, or Magnitude and Continuous Phase. We can put in something here, so Series, Fed, Cylindrical, Coil. Okay, then we're opted. Now it's going to save a touchstone file, which is particularly useful because that is actually the S11 data. I could load that into anything that's compatible with a touchstone import of data. So then I'm going to, like this, as series fed, cylindrical coil, and I'm going to put, I'll just leave it as that. Just going to save that on my desktop. Save, and that's put that file on my desktop, and I could reopen that. So if I take an example, I just disconnect the VNA, take a single sweep, so that's it. My data is not there anymore, and now I want to actually look at that data again. Now I particularly come in here, and I like to use the open drag drop target. So I open that, and that allows me to load a drag and drop data files onto one of these ones that I want to see. So what I'm going to do now is I'm from my desktop, I'm going to go and I'm going to drag that onto S11. There, let's just move this out of the way for the moment. Okay, now we can see I've got my data back exactly as I had it before, and I can save that for any of the data. So that also shows how to actually save the data. Okay, so that really gives an introduction to how to use the VNA software to do this kinds of measurements on Tesla coils. If I had another pair of coils connected by the single wire medium, then we would start to get some of the types of data that are shown in other posts that I take. But this is an introduction to using the software to measure Tesla coil and TMT systems. And in subsequent posts, I'm going to be looking at coming back to also comparing with the HP 4195A professional vector network analyzer, and also having a look at transmission and through measurements, so S21 and ultimately Z21. Okay, great, very good.